This is Unit 4, Topic G. We're now going to look at integrals that involve the inverse trig functions. There are 3 of them that we'll use. They're all listed here, and I'll also mention that they're also listed on your list here. I did happen to use the inverse instead of the arc sign, arctangent and arcsecant, but of course they mean the same thing, right? This would be the same as saying arcsine, x over a plus c, and so on. Arctangent, arcsecant. Right? There is one typo here in the notes. I'm going to have you fix it right now. It's correct on your list, and that was the arctangent. You'll notice that on your list, the arctangent integral has a 1 over a out front here, and I accidentally left that off when I typed here, so if you would go ahead and add it to your notes, that would be great. All right, we're going to use these 3 integrals as givens and see if we can figure out how to do some integrals based on them. So I'm going to start here in number 1 with 3 over x squared plus 16 dx. When I look at these 3 forms, there's no radical in this one, so it really needs to be the arctangent. In this case, if I wanted to make it look just perfectly like the one that I have, I could rewrite this denominator and put the 16 in first as a 4 squared plus x squared. And actually, I probably could have done one more thing. In fact, maybe I should just do it right now. Why don't we go ahead and pull the 3 in the numerator right out of the integral. I'll just put a 1 up here, and I'll bring that 3 out in front. This now is perfect. It looks just like that, with an a value of 4. And so I'm going to get 3 times 1 over a, 1/4, times the arctangent of x over a, so x over 4, plus c. And other than multiplying the 3 times the 1/4 and getting 3/4, that's done. So it was just a matter of making what I was given a perfect match for the formula. That's the easiest, most straightforward situation. Let's look at number 2. This one we have a little bit more work to do. I am going to go ahead and compare this. I'm going to use my list here just so that I don't have to keep on going back and forth, pushing my paper up and down. And I'm going to say, whoops, let's do it like this. Here I do have the radical in the denominator, and under the radical I have a constant times, that is a perfect square, right? It's x squared squared. So as I compare here, I think it's probably going to be closest to this one, the constant minus the x squared. Let's see if we can get it to match that form exactly. In order to do that, the first thing I'm going to do is try a u-substitution. Now this is going to be a really special u-substitution. Specifically, in order to use the formula, I need that term to be something squared. Since that's x squared squared, I'm sort of thinking of this as the square of x squared. If I let u equal x squared, then that'll be 5 minus u squared, and I'll have a nice match for my formula. So let's try it. Let's let u equal x squared. Du dx would be 2x. And I get 1/2 du is equal to x dx. The u this time is just the x squared. So on the bottom, under the radical, I have 5 minus u squared. Now this x dx, I'm going to replace with the 1/2 du. And I'm just going to bring that 1/2 right out in front here. And I'll put the du right on top of my fraction. And this is now a pretty darn good match for that arcsine integral. Got the 1/2. And then remember, under the radical, I was supposed to have a squared minus x squared. I can fix that pretty easily just by making that 5 the square root of 5 squared. So my a is actually the square root of 5. So, according to my integral, I'm supposed to get the arcsine of x over a. For me, that'll be the arcsine of u over the square root of 5. So it's all about getting your integral to match the form that we need. All right, other than replacing the u by an x squared, I'm done. All right, let's try another one. E to the x over e to the 2x plus 1. If I'm going to get that to look like one of my inverse trig integrals, it did not have any square root in the denominator. So the only possibility is going to be this one with the inverse tangent. Denominator is supposed to be a squared plus x squared. So let's see. I need to write that as something squared. I could think of that denominator as e to the x squared plus 1, so that when I multiply the exponents, I get back to e to the 2x again. That suggests to me that I might want to let u equal e to the x, so the denominator can just become u squared plus 1. So let's do that. Let's let u equal e to the x. Du dx will still be e to the x. And du is e to the x dx. So this is what I wanted to make my u. Even though there's another e to the x up here, I'm going to save that. That e to the x dx I'm going to use later as part of the du. So in the denominator, I now have u squared plus 1. And then my e to the x dx can just become du. All right, I think we're in pretty good shape here. This is supposed to match this arctangent integral. I've got a u squared instead of an x squared, which is fine. The other term is supposed to be a squared, but 1 is the same as 1 squared, right? So I'm just thinking a is 1 here. So my integral should be 1 over a, it's 1 over 1, times the inverse tangent, or I tend to like to write it as the arctangent. And this says x over a. For me, that's going to be u over 1 plus c, which gives us the arctangent of u, which is e to the x, plus c. So the trick for doing these integrals with the inverse trig functions is really being very strategic as to how you pick your u values. You've got to create the u values so that one of these forms is what you get. All right, we'll see a couple more like this in the context of these last few problems. Just like there was a common algebra trick that we used with the natural log integrals, there's also a couple of actually common algebra tricks that get used with these. One we've actually seen before, the trick of separating a numerator. If I want this integral, I could actually turn this into two integrals. 4x over the denominator plus 3 over the denominator. So I'm going to go ahead and do that. All right, let's see what we got here. I have a 1 minus x squared under the radical, and there's two things that makes me think of. One possibility would just be to let u be 1 minus x squared, and the other possibility is that's also the denominator in the arc sine integral. It's going to turn out that I've got one of each of these. Let's take a look and see if we can tell which is which. I'm going to start my u substitution and see what happens. If I let u be 1 minus x squared, that would be the inner function, what's under the radical, then du dx is negative 2x. Du is negative 2x dx. And negative 1/2 du is equal to x dx. Right. So, which one is that going to work for? That's actually going to work for this one, because I have an x dx to work with. Oops, I forgot my dx over here. But it won't work here because I don't have an x, right? I have a dx, but I don't have an x. So this u substitution is actually going to be useful specifically for that integral. So let's do that one first. I'm going to bring the 4 out in front. My denominator is the square root of u. And then I'll replace the x dx with negative 1/2 du. So let's see, I'm going to put the negative 1/2 out in front and the du right there. That would be negative 2 times the integral of, that's really u to the negative 1/2 du, or negative 2 power rule here, u to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2. So I'd have negative 4 times the u, which is 1 minus x squared, to the 1/2. Okay? So, all very well and fine on that one. Now we have to figure out the other one. I've already seen the u substitution won't work. So I'm hoping that I can go back to that arc sine integral, and I think we will be able to. Let's see if I can get these both on the same page. There we go. This looks like an almost perfect match already. I can always pull the 3 out of the integral. 1 squared is still 1. And I've got the x squared. I don't even really need a u substitution on this. I'm really ready to go. Let's pull the 3 out. And we'll just remind ourselves that 1 squared is the same as 1. So I have 3 times. This would be the inverse or arc sine of x over a. In this case, that would just be x over 1. And I'll put my plus c in since I'm now at the end. So putting my two pieces together, my final answer is going to be negative 4 times, 1 minus x squared to the 1/2 plus 3 arcsine x plus c. So keep in mind that strategy of separating a numerator, writing it as two separate fractions, and then treating each fraction as its own integral. It's a common trick for these. The other fairly common trick is completing the square. When I have a problem like this one, I'm looking at that thinking there's not a whole lot I can do, right? I can't separate a denominator, only a numerator, so I'm stuck with this being all one fraction. And it's pretty clear to me that a u-substitution, with u being the denominator, isn't going to help, right? The derivative would be 2x plus 4, and I definitely don't have anything like a 2x plus 4 waiting for me up in my numerator. So, nothing that we've talked about so far is going to work. When I have something like this, what I'll often do is try to complete the square in the denominator. I have x squared plus 4x. I'm going to kind of separate that off because that's what I'm going to complete the square on. And then I still have this plus 13 out here. Completing the square, I'd have to take half of the 4, 2, square that, plus 4. Now I can't really change my value, so if I add 4, I also have to subtract 4, so that I haven't really changed the value of my denominator. This is now x plus 2 squared plus 9. All right, have we accomplished anything? Well, if you look at this, would you agree that there's the potential to match this arctangent integral? X plus 2 squared would be kind of like the x squared. In fact, I'll probably let u be the x plus 2. And of course, 9 is 3 squared. So I should be able to get a good match for that arctangent integral. Let's start by letting u equal x plus 2. So du dx is just 1, and du is equal to dx. My integral then, I'll replace the x plus 2 with u, so this is u squared. And just because I kind of know where I'm going with this, I'm going to write the 9 as 3 squared. The dx just becomes du. I now have a really good match for this integral. So I'm going to get 1 over a. Notice here that my a is 3. So I'm going to get 1/3 times the inverse tangent, or I kind of like writing the arctangent better, of x over a. That will be u over 3 in my problem, plus c. All right, we're almost there. I have 1/3 times the arctangent. U was actually x plus 2, and that's over 3, plus c. All right, one more. That 5 over the square root of 4x minus x squared. This sure reminds me of these inverse tangent or inverse trig functions with that radical in the denominator. The problem is, if you look at these, this has got a linear term, right? It's got a 4x. And this one with the radical in the denominator doesn't have any x to the firsts. And there's no x to the first under the radical in this one either. So that 4x is a problem. Once again, I'm going to turn to the idea of completing the square to see if I can fix the problem. I'm going to pull the 5 out of the integral right away. And under my radical, if I want to complete the square, I have to have just a positive 1x squared. So I'm actually going to factor a negative out and then make that x squared minus 4x. All right, under my radical and inside the parentheses, I'm going to complete the square. Half of negative 4 would be negative 2. Square that is positive 4. And here's a place to be a little careful. Because of the negative, the 4 that I put in is really a minus 4. So to counteract it, I'm going to have to put in a plus 4. Minus 4 and plus 4. I still have this dx. Put that right over here. All right, so what have we got? Under the radical, we have got minus, that's x minus 2 squared, plus 4. Okay. I think with just a little bit of rewriting, that is going to match this pretty well. Let's go ahead and put the 4, which is the a squared. We'll put that first, so I'm just going to reverse the order here. I'm going to write that 4 as a 2 squared, that's positive, and then minus the x minus 2 squared. If I let u be that x minus 2, I think I'm going to get exactly what I need. So we've got 5 times the integral of 1 over the square root of 2 squared minus, this is now u squared, and the dx can just become du. So I have 5 times, and notice when you now match this with the arc sine integral, my a would be the 2. So I'm going to get the arc sine of u over 2. Plus c, or 5 times the arc sine of x minus 2 over 2 plus c. So again, with these inverse trig functions, the goal is always going to be to manipulate what you need to, whether it's completing the square, a u-substitution, just rewriting, to get a form that matches one of these 3 exactly. All right, that brings us to the end of our topic G.